and start recording this part. This is the actual lesson. This is what we want to take away from our work today. And so let's go ahead and do this. So Carter, since I got you on the hook here, big idea here. When you took that voltmeter, and we'll review series circuits in just a minute, and you played around with the voltmeter, what did you notice about the voltage at the 5 ohm, the 10 ohm, the 15 ohm, and the battery? What was the voltage doing?
It had the same voltage for all of them.
Super cool. All right. So the voltage for the entire circuit, and if you guys can go ahead and just mute for a couple minutes here, I'd appreciate it. So if we go and say that, hey, you know what, voltage is going to be the same everywhere. That is a huge idea. So the voltage at the first resistor, the voltage at the second resistor, the voltage at the third resistor, the voltage is the same everywhere in a parallel circuit. Now, when we talked about series circuits, and thanks a lot for that, Carter. When we talked about series circuits, I'm going to come over to Addie. Addie, can you remind me what was the same everywhere in a series circuit?
Current.
Say it louder. I think I heard you.
The current.
Yes. So we have different rules depending on what type of circuit we're talking about. So in a series circuit, we said that it was the current that was the same everywhere. Parallel circuit is a totally different game. It's the voltage that's the same. The reason for that, all right, is actually pretty easy if you can go back and think about, and thank you, Addie, if you think about what voltage is related to the amount of energy that these charges have. So I come into the battery, all right, the battery jumps me up to 10 volts. It gives me 10 volts of energy as I pass through the battery. And now as I'm moving along here, and I'm going to go over to Annie Brickley, does it take much energy to go through the wire here that I'm kind of moving along with in my pen here? Does that take much energy?
No.
No, because there's literally no resistance in a wire, virtually none. So I come out of the battery with 10 volts of energy. I've got 10 volts of energy, and now I come to a junction. Annie, I'm still with you here. In a series circuit, how many paths were there for the charges to flow in?
Just one.
Just one. How many distinct different paths from this side of the battery here to this side of the battery here? How many different paths do you see?
At least 3.
Yeah, I totally see a path that goes through the 15 ohm resistor back to the battery. I see a path that goes through the 10 ohm, and then I see a path that goes all the way up through the 5 ohm and back down. So I have multiple paths. Now let's come back to it here, Annie. I used up no energy getting to this point. You have a decision to make. Which resistor do you want to go through, Annie? Your choice.
10.
Okay, so I decide this is the path that I want to take. I'm going to go through that 10 ohm resistor. And so how many resistors did I end up going through? Just the 10, or did I go through all of them?
All of them?
If I did that, then I might have to do something like this. So I go through the 10, and then instead of going back to the battery, I'd have to maybe kind of make a weird loop. So it turns out that in a parallel circuit, all right, what you're going to do is you're going to have multiple paths. And so here's the issue. I'm actually only going to go through that 10 ohm resistor, Annie, on my way back to the battery. So if I have 10 volts worth of energy, and the only thing that I do is I go through that 10 ohm resistor, I get to use up all of that 10 volts of energy to go through the 10 ohm resistor. If I switch my gears here, Annie, and instead of going through the 10 ohm, I went through the 15 ohm, same deal. I'm only going through the 15 ohm on my way back to the battery, all right? So I have all of that voltage, all 10 volts available to use up depending on which resistor I go through. So here's the key takeaway. The voltage is going to be the same everywhere in a series circuit. Once you understand that, then the next piece of the puzzle will actually make decent sense, all right? Now, let's go to, let me see who I've got here. I think Emily Larson. Thank you, Annie. Emily, can you tell me a little bit about what you saw with the currents? Just kind of summarize what you saw.
I didn't really do it because I have a weird setup.
Okay,
But I'm
that's
guessing
okay.
the current, I don't know, probably like, yeah, I'm not the best person to ask.
That's okay. I appreciate that. Let me ask, for the sake of time, because I know that we do have a short amount of time here. Ethan, did you see anything going on current-wise there?
Yeah, for the 5 ohm resistor, I saw it was like it had 2.
Okay, I'm going to write those numbers down. So I had a 2 amp current up here. Did you know how much current was going through this 10 ohm resistor?
1 amp.
Okay. And how much current did you see going through the 15 ohm resistor?
It was like 0.67.
Which is basically 2/3.
Yeah.
Okay. Now, think about why that might make sense here, Ethan. Where did we see the most current through the path that had the what resistance?
The
The most current was through the path that had the
lowest resistance.
lowest resistance. Let's see if that makes sense. Much of the electricity went the easiest way. That kind of makes sense, doesn't it? All right. So we see that if all three of these things have the same voltage, which we saw, right? Since we know that current is equal to voltage over resistance, as the resistance gets smaller, the current has to get bigger. All right. So the really cool thing about this is I totally agree with these numbers, and I'm hopeful that those of you that did play around with it saw those 3 numbers. Now I'm coming back to you, Ethan. Did you happen to notice how much current was flowing down here in this part of the circuit?
Like 3.67, I think it was.
Okay, and that's absolutely right. Now, do you see that that number connects to these numbers in any meaningful way? How could I take these 3 numbers and get 3.67?
The sum.
Bingo. So here's the big deal. If I think about current in a parallel circuit, the current is what adds up, all right? So we've kind of switched the rules completely with parallel circuits as opposed to series circuits. For parallel circuits, it's the current that adds up, and the voltage is what stays the same. Whereas if we go back and we recall with series circuits, it was the current that was always the same. And Ethan, since I still got you here, I think, what was one of the things that added up in a series circuit?
The voltage, or
The voltage was absolutely something that added up. So the voltage at resistor 1 was plus the voltage at resistance 2. So we've got this sort of separate set of rules for parallel circuits than we had for series circuits. And since we're looking at series circuits, don't forget that if I ever wanted to, Ethan, thank you, if I ever wanted to find the total resistance of a series circuit, it was wicked easy. You just literally add up the resistors together. Now, we don't want to get too far into the weeds because we're just about out of time here, but the total resistance for a parallel circuit, and this for me when I was a kid, when I was a young person first studying physics, this is where my mind kind of just, I lost it. I was like, this doesn't make any sense. It turns out that if I want to know the total resistance for a parallel circuit, I have to go with kind of a weird formula. It actually is this: 1 over R total is 1 over R1. And I'm just going to get this to you. We're going to look at some videos and some work where we practice this and get a little better at it. There's this sort of reciprocal relationship. All right, go ahead and jot that down. The big takeaway is simply this, all right? As you add resistors in parallel, the overall resistance of the circuit decreases. And like I said, this is where my brain kind of just exploded when I was trying to first understand circuits when I was a young person. Because I'm literally saying, if I were to add more resistors in parallel, that actually lowers the resistance. Now, I'm going to try to get this into your brains a little bit here, and then we're going to call it a day. All right. Here's the thing. If I have a highway and I want to carry as many cars as I possibly can carry, all right, here's my 1-lane road. I can only carry a certain number of cars per second. The easiest way to increase the number of cars is to build a highway that has multiple lanes. And the more lanes that I put in this highway, the more cars I can carry. So what's the analogy here? If I only have one resistor, all right, I only have one path for the electricity. So relatively speaking, I have a pretty high resistance. As soon as I add another lane, I add another path for that electricity to take. So what that's done is that's decreased the resistance because I now have more cars flowing, right? The cars and the electrons, that's the analogy. And so as you add lanes to your highway, you're adding more and more paths for the electricity to travel. And since I have more electricity traveling, there's less resistance to flow. So this one is the highest resistance. This one is sort of medium resistance, and this is the lowest resistance. So parallel circuits are tricky for students, all right? And with that, I think I want to go ahead and stop recording.